I guess.
I love how like today they said it's open, but everyone canceled. Like you can't just set it for 2 days.
Yeah, I know. They gotta stop doing that shit. They're like-
It's so annoying.
they're just fucking with us.
They're like, oh, we care about your safety. All right. Makes it mandatory to come on like the heaviest day.
Yeah.
And then like. She got. Fine, get your ass back. Compared to yesterday.
Today's worse. Today's worse,
Yeah, I
right?
feel like the morning was worse.
I was hydroplaning and driving on the freeway here.
Oh, I had to west for like a second.
Oh, man.
I took the normal roads and then it was just flooded on the innermost lane.
I would have taught from home today too, but I didn't have my iPad, so I had to come here for that anyway. So I'm like, I might as well, because if I taught from home, they would have charged me a sick day, and so
Really?
like I might as well just stay here.
That's so stupid.
Yeah.
And for me, we had senior design, but like they didn't say anything.
Uh-huh.
He showed up and like nobody pulled up. I was like sick.
Oh wow.
So. Yeah.
Oh, so he canceled. He didn't say anything.
Yeah, a lot of people said that they have the option to be on Zoom.
Yeah.
That's been.
Keeping around
Yeah.
what you just said.
Oh, I see. I see.
We're waiting out the rain.
Hopefully, yeah. It seems like it's gotten a little better.
I went out and it was fine. There's just so many potholes now.
Oh, I bet. Yeah.
I had to like change lanes like 5 times in one.
Jeez.
The big old pothole. Is it your credit point for showing up?
No.
So is this a new section from last week?
Yeah. No, we're finishing up the one from last week, and then we're starting a new one maybe halfway through today.
I asked you if you were waitlisted in a class, but I never dropped it.
Mhm.
Does it automatically, like, and you never got in, does it just drop on its own?
It just drops on its own.
Okay,
Mhm.
because I'm still technically on the waitlist as of right today,
Yeah.
but I can't drop.
Oh, because it's past the deadline. Yeah, it just doesn't show up on your TDA at all. Yeah. So it says if you dropped it without withdrawing, so no harm.
I mean, I've never been on, so I could take a W if I have to, but that's what's true, but.
Yeah, better not. Better not.
Yeah, I'd rather not. It's not us, it was only easy for next class,
Yeah.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, staying dry, hopefully. It's a mess out there. It's wet. So yeah, hopefully for those of you here in person, hopefully you guys get home safe. It's a little dangerous driving out there. I was talking to someone before. I don't know why they made us come here today when they didn't make us come here yesterday, but I don't know. It's all a mess. But hopefully you guys stay safe, stay dry, and you know, take care of yourself. Okay, so the plan for today's just another lecture day. So we have a bit more notes to finish up from last time about Murray's Law. So I think we'll probably spend about half the lecture on that. And then the other half of the lecture day, we're starting a new topic, kind of more kind of linking kind of what we've been talking about in terms of fluid mechanics and talking about how that affects the biomolecular side of the arterial system. Okay, so it's going to be arterial biomechanics. That's the next topic. So a little bit about our plans for the next week. So this week is just I'm just planning on just doing lectures this week. Next week is going to be an interesting one. So next week on Tuesday, I have lecture slides for you. So it's not a traditional lecture. We're going to be talking about medical imaging technology. So talk about X-ray, CT scans, MRI scans. And the reason I want to do that next week is because next Thursday, we're going to be doing our first workshop in Cardiovascular. So we're going to be learning how to use the new software. We're going to be focusing next Thursday on the geometry construction. And so what we're going to do next Thursday is that I'm going to show you how to download the software. I'm going to show you how to install it. And we're actually going to load in someone's CT scan. So this is a real life person's CT scan of their aorta. And we'll learn how to create basically a CAD model of that aorta model using Cardiovascular. Okay? So next week's kind of like a little bit of a break. You know, we're doing mostly theory, mostly concepts the last couple of weeks. Next week will be more kind of hands-on and stuff with the software. And then next week, you know, we'll talk a bit about kind of what your overall project is going to be, and we'll start kind of working on that the next week after that. Okay. All right, so some announcements. Remember, the first homework assignment is out there. After today, you should be able to do all of it. And that is due this Friday or Sunday, I think. So make sure you get that done. And then I'll have the next homework assignment ready for you probably sometime next week. Okay. Any questions I can answer before we get started for today? Everyone have a good weekend? Hopefully stay dry this weekend. I had a great weekend, actually. So on Saturday, I went to a show with my wife called Trilogy in LA. It's by this DJ named Millennium. My wife loves him a lot, so and she's been wanting to go to a show with me. So I finally went to one with her. I was able to go with a few of my really good buddies too. So it was a great night. And it made me think, you know, because as you get older, it's much harder to have those kinds of experiences with your friends. Just because everyone just gets busy with kids and work and family obligations, stuff like that. And so to go out, good friends, have a great time. It was special. And so it reminded me that, take care of your loved ones, text them, say, care about you, thinking about you. People always think it sounds weird, but it's always really appreciated. And so, it was a great night. I think it helped that I had some other things in my system to help me feel a bit more sentimental than normal. So but we all had a great time. So it was in SoFi, yeah. Long drive. Parking was terrible, but it's one of those things that we want to experience before, because a lot of us are thinking about having kids soon, and so we wanted to have these kinds of things and travel while we still can. Okay, so let's go ahead and pick up where we left off last time. I went Saturday. One of my friends actually went both nights. He went both Friday and Saturday. So he was yeah, Sunday he was very dead. So but I only went Saturday. Yeah. Yeah, no, yeah. What yeah, I was 100 level. I was my wife actually had 4 tickets, but then she spent most of the night in the 100 level with me. Oh, nice, awesome. Yeah, it was great. I'd never been to one of those, so it was an experience. It was an experience for me for sure. Yeah. Okay, so let's pick up where we left off last Thursday. So last Thursday we were talking about Murray's Law. Okay. So just to kind of refresh your memory, Murray's Law is has to do with bifurcating vessels, okay? And so a bifurcation happens when you have one vessel that splits into two or more vessels. And so even though it's possible to bifurcate into more than two vessels, for the most part, you're going to see bifurcations of two. And so remember what we talked about, the one, and flow is usually going, from left to right here. So we have one vessel that's coming like this, and then flow is coming out like that, right? So the vessel that's on the left here that kind of spawns the two smaller vessels, this is called the parent vessel. And these two are the daughter vessels. And what we were talking about was that, all these vessels have a certain size, right? And if we roughly assume that the blood vessels are all cylindrical, then we can characterize their size by simply their radius, right? Okay. So we have the radius of the parent vessel, we call that RP, and then we have the radii of the two daughter vessels, RD. Okay. So the two daughter vessels don't necessarily have to be the same size, but for simplicity, we're just going to assume it is. Okay. And what we want to know is that based on fluid mechanics, is there a relationship between the size of a parent vessel and the daughter vessels whenever a bifurcation happens? Okay. All right. And so this relationship is going to be based just kind of purely on all the fluid mechanics stuff we talked about last Thursday. So talked about its velocity distribution, we're talking about its flow rate, the pressure, right? And so if we characterize the fluid mechanics, we can come up with this relationship. Okay. And so what we started saying was that a lot of this in terms of this relationship, a lot of these things in general are kind of motivated by power and energy. Okay. And so what we talked about kind of near the end of class on Thursday was that the power and energy needed to drive kind of blood through the cardiovascular system mostly depends on two factors. Right. So the first factor that we talked about was viscous friction forces. Okay. So whenever you have any kind of motion, whether it's solid mechanic motion, fluid mechanics motion, friction's always going to have an impact. Okay. Friction isn't the best way to describe it for fluid mechanics. Really, it's just viscous shear forces. But the idea is the same. So when you're kind of pushing fluid through a surface, there's something kind of holding you back based on viscous shear, and it acts very much the same as friction. Okay. All right, and so what we said is that as your vessel radius decreases, the viscous friction forces are going to go up. And so the smaller your vessel, the smaller your tube, the higher your viscous forces are going to be, right? And so the smaller tube that you have, it gets much harder to squeeze through it because those viscous forces kind of go all the way up. Okay. The second aspect that kind of affects the power and energy that's needed to drive flow forward is inertia. Okay. And so just due to the fact that blood has mass, it has a density, it takes energy to kind of move that mass forward and back. Okay. And so the energy that's needed to tackle inertia goes up as the vessel radius increases. Okay. And so as your blood vessel radius increases, that just naturally just increases the total amount of mass that's in the blood vessel. And the more mass that you have, the more inertia that you're going to have as well. Okay. And so I put these two factors here, and I kind of juxtapose them to kind of show you that these two are competing. Okay. Because ultimately, what you want to do and what your cardiovascular system wants is that it wants to find the perfect size for your blood vessels to minimize the energy costs. Okay. Because the human body, just like literally everything else in the world, is lazy, and it wants to do kind of the bare minimum or expend the bare minimum amount of work in order to get the job done. Okay. People always talk about that as if it's a bad thing, but that's just smart, right? So if you can get the job done with the least amount of effort, least amount of energy expended, that's generally a good thing. And through evolution, that's generally going to be good, because then you can save your energy for other things like outrunning lions and or whatever our ancestors had to do. Okay. And so we're gonna take this idea and kind of run with it. We're gonna connect it to kind of the fluid mechanics of what we talked about last time, put some equations on this, put some math, and then we'll get an expression of Murray's law. Okay. But that's basically where we ended up last time. Just wanted to recap that. Any questions on this here? Okay. All right. So let's kind of run with this idea. And so let's come up with expressions for each of these two factors and see how they can kind of compete. Okay. All right. So let's characterize the viscous forces first. Okay. So let me go ahead and draw my blood vessel here. All right, so what I have here is just a representation of a blood vessel. We have its radius r, and we'll assume that it has a length L. All right. All right. So viscous forces or viscous shear forces are mostly active near the walls. Most active. Okay. If you think about how friction works for solid objects, friction is a surface force. And so whenever an object makes contact with another object and you're trying to push that object while kind of rubbing against that other object, that's where friction comes into play. Okay. And so viscous forces are the same. And so when your blood is making contact with the with your blood vessel wall, there's going to be viscous force. There's going to be friction forces there. Okay. And so as your blood vessel kind of reduces in size, the proportion of fluid that's in contact with the wall goes up, right? So if you have a big vessel like this, right? Let me kind of erase these. Okay. Only the fluid that's kind of on this layer of the vessel wall, that's going to be the one that's primarily going to be experiencing the viscous forces. But if I were to draw a smaller vessel, okay, like this, right? Right, and again, we kind of trace out the exterior or the surface of that. You can see that it takes up a bigger proportion of the vessel. Okay, because it's a little bit counterintuitive to understand, you know, because on the one hand, if you have a bigger vessel will give you a larger surface area of the vessel wall, right? And so if you look at the statement that I posted previously, where, you know, it says that viscous forces go up as the vessel decreases, right? That might seem a little counterintuitive because, you know, as you decrease the vessel size, you're actually reducing the surface area, right? But what's actually important here is not the raw surface area, it's the ratio of the surface area to the volume of the vessel. Okay? And so for the smaller vessel here, the ratio of surface area to volume is higher. Okay? Right. And so one thing we'll talk about a lot more in later chapters, that, you know, when you have fluid that kind of flows past a wall like this, you know, what we typically say in the fluid mechanics world is that the information about the wall, or you know, the viscous shear forces from the wall propagates to the middle of the vessel wall, kind of like this, right? And the smaller your vessel is, kind of the faster or the more easily that information kind of propagates to the center. Okay. And so as your vessel gets smaller and smaller in terms of radius, because of the cylindrical shape, that ratio of surface area to volume is going up. Okay. And so that's why as you decrease the vessel radius, you feel these viscous forces, or they become a lot more significant, you know, the smaller your vessel is. Okay. Okay. So that kind of explains a little bit about that trend that I mentioned up there. So to overcome these viscous forces, because ultimately, you know, your heart needs to push the blood past these vessels, so these viscous forces must be overcome. Okay, the main way that this is done is through pressure forces. And so it's not that different from, you know, from flow in your faucet, right? Whenever you have flow that's kind of internally bounded, it's kind of bound by all sides. Usually those are pressure driven flows. Okay. And so ultimately what that means is that, you know, if your flow is going from left to right, okay, that means that, you know, on this surface right here, we have a force that's being applied here. In red right here, these are the pressure forces from the heart. Okay. We have a force that's distributed across that cross section of the vessel, right? And that's the force that kind of pushes that flow forward. Right? And so we can characterize that pressure force. And so if we assume that pressure is kind of uniform throughout the vessel, Because the pressure is nothing more than just the force distributed over an area. And so what we can say is that the pressure force is given by delta P times A, where A is the cross-sectional area of that vessel. All right. So that's the force, that we're going to consider for this part here. Okay. All right. Any questions on this so far? Yeah.
When we're looking at like pressure drop, is it stay like relatively uniform throughout the entire like circulatory system, or is it like the further away you get from the heart, it like kind of like starts to fluctuate a little bit?
Yeah, no, that's a great question. It depends on actually the local size of the vessel. And so for this case where our radius is basically constant, we have basically a tube with the same radius. The pressure drop is pretty linear. But in reality, you have blood vessels that kind of vary in size. Generally, what happens actually is as you get further away from the heart, the blood vessels what we say is that they taper. And so they kind of become smaller in radius. And so the pressure drop kind of accelerates as you get kind of down towards the ends. Yeah. Mhm. All right, any other questions on this? Okay. All right. So now that we have the force, we need to convert this into a power. Okay. And so one way to obtain power is that you take a force and you multiply it by the velocity of the object that it's driving, right? And so in this case, we have our pressure force, and the thing that the pressure force is exerting on is the blood. Okay. And so one way that we can obtain power from this is to take this pressure force and multiplying it by the mean velocity of the blood that's flowing through the vessel. All right. And so power. So I'm gonna denote power like this. And so usually we use the simple W for work. And so W with a little dot on its head is power. Okay. So the power that's related to the viscous forces is equal to the pressure force. So we have delta P times A. So this right here is the pressure force. Okay. Multiplied by, I'll call it U bar. Okay. So this U bar is the mean velocity. Okay. Pretty straightforward. I'm going to group these terms a little bit differently. And so let me take delta P, going to move it off to the side there. And then we'll move the parentheses around A times U bar. Okay. So we have the product of the cross-sectional area multiplied by the mean velocity in the blood vessel. Okay. And so what this is right here, we have cross-sectional area multiplied by mean velocity. This is our flow rate, our volumetric flow rate. And if you remember from last Thursday, we gave this symbol Q. Okay. Q is typically the symbol for volumetric flow rate. Okay. And so if we plug that in, we get the power related to the viscous forces is equal to the pressure drop across the vessel multiplied by its volumetric flow rate. Okay. So pretty simple expression at the end of the day. Because pressure drop is something that's easily computable, and the flow rate is also something that's relatively easy to measure. Okay. Right. So conceptually, this is really nice, right? So this is kind of a nice compact expression. But ultimately, we want to get something that's in terms of the radius, right? Because ultimately, we want to work this. We're gonna want to work this back to Murray's law, and Murray's law is an expression about radius. Okay, so we're gonna plug in for something. So let's plug in for the delta p, right? And the delta p, we're gonna use an expression that we derived from last time. And so actually, let me put it here, just because it's been a while. And so last time, just based on Navier-Stokes, we got an expression that delta p is equal to 8 mu times L divided by pi r to the fourth multiplied by q. Okay. And so we obtained this from Navier-Stokes. In particular, integrating the Navier-Stokes across the cross section. Okay. All right. And so we plug that in, we get 8 mu L divided by pi r to the fourth multiplied by q. We multiply by another q that was already present. And so we get our final expression here. We get the power that's needed to overcome viscous forces is equal to 8 mu times L divided by pi r to the fourth multiplied by q squared. Now, this is an expression we can work with because it has the radius. We've gotten rid of one relative unknown, which is the delta p. And we got this in terms of q. And we'll see that q is actually really nice because we can use conservation of mass in kind of a simple way in order to derive the Murray's law. Okay. All right. So any questions on how we obtained this result here? Okay. Actually, let me label this expression. So this is the power needed it's this expression. Okay. All right, so let's table this one. So now that we have this expression here, let's table it for a second, and let's come up with an expression for the inertia. Okay. Right, because kind of our argument that we started with was that the power needed to do this must be balanced with the power needed to overcome inertia of blood. Okay, because if you look at this expression, right, for the viscous power, you can see that we have r to the fourth in the denominator, right? And so if we wanted to minimize this, and so we wanted to minimize the viscous forces, the best thing to do would be to make r as big as possible, right? And so if you make r really, really big, because that r to the fourth is in the denominator, that minimizes our viscous forces. But we all know, right? And so we all know that people aren't walking around with, 1 meter diameter blood vessels, because that would look ridiculous, right? So there must be another factor here that kind of balances this out to get our blood vessels as small as they are. Okay. So inertia. All right. So the power needed to overcome inertia. In reality, it's complicated with fluid mechanics. We'd have to go back to Navier-Stokes if we wanted to give it a real good treatment. And so we're going to use kind of the science of approximations here, just kind of for the sake of brevity, because I don't want to distract too much from the Murray's law. And so what we're going to say is that the power needed to overcome inertia is going to be proportional to the volume of blood within the blood vessel. So that was kind of the argument that we started with. So the more blood that you have in your vessel, the more mass there's going to be, the more inertia that you need to overcome. So, you know, the logic kind of checks out. It's just we're kind of skipping all the complicated math and physics along the way, right? And so what we can say is that the power needed to overcome inertia is equal to the volume. Okay, so this capital V here is the volume of blood in the vessel. Okay, multiplied by B. Okay. And what is B? B here is our proportionality constant. So B is some kind of scaling constant. You know, its exact value depends on, you know, Navier-Stokes and physics and all that stuff. And we can go through the whole thing to determine what B is. But for our purposes, it's not really necessary. And so what we're going to say is that, you know, B is just some constant. Okay. In the end, it's not going to matter. You'll see, but you know, we're just going to assume that it's there. Okay. All right. So we can plug in for this, and so we can do a little bit better than V here, because we know what our geometry is. Our geometry is essentially a cylinder, and so the volume of cylinder is pi times the radius of the cylinder squared multiplied by L, and that's going to be multiplied by B. Okay. And so that's going to be the power that's needed to overcome inertia, roughly, right? With up to an arbitrary constant. Okay? Or it's not arbitrary. It's just, you know, we're leaving it arbitrary. All right. So now that we have our two contributions, we have our contribution to from the viscous forces, and we have our contribution from inertia. In order to compute the total power, we just have to add these two together. So it's going to be W tot is equal to W viscous plus W dot inertia. Okay. And so we plug in for these, we get W dot total or tot is equal to the viscous contribution, which is 8 mu L divided by pi r to the fourth q squared plus pi r squared L times B. Right. So we're getting somewhere. Any questions on this so far? Yeah.
Is the proportionality constant like something that's specific to like cardio systems, or is it like something just fluid mechanics in general?
It's just fluid mechanics in general. So it depends on the geometry. And so in this case, it's going to depend on the cylindrical coordinates. And so you can derive it from Navier-Stokes. So it's just kind of something in general. Yeah. Mm-hmm. Okay. All right. And so now that we're at this point, we have an expression here for the total amount of power, right? And you can see here we have two terms, right? In particular, our first term here has an r to the fourth in the denominator. And our second term here has r squared that's kind of up top, okay? And so we have two competing terms, just exactly like we predicted, okay? And so let's take this expression and find the optimum radius, okay? And so to find the optimum, we can take the derivative of this expression. So we want to find the radius, or find the value of r. Okay, so we want to find the value of r that minimizes the total power. And so we can do this simply since we have just a one-dimensional one-dimensional system here. Okay. So let's take the derivative of this with respect to R. And so we take the derivative of that first expression, we get a minus 32 mu L divided by pi R to the fifth times Q squared plus 2 pi R L B. Okay. And then once we take the derivative, we can set it equal to 0. Okay. All right, so that's kind of the traditional way to find the minima of a one-dimensional function. Okay, you take its derivative, you set it equal to 0. Now we can solve this expression for R. All right. So from here, it's a bit of algebra. It's not too hard, but I do want to kind of move on to the next thing. So I'm going to go ahead and skip to the result. Okay. But you can definitely verify this on your own. It's just a couple steps in the notes. Okay. And what we find is that the R minimum, I'll just say big R, is equal to quantity 16 mu Q squared divided by pi squared B raised to the 1/6 power. All right. And so in order to minimize the amount of power that your heart must exert in the cardiovascular system, the radius must be this. Okay. So it's a function of the flow rate, it's a function of viscosity, pi. Okay. And there's a 1/6 power in there. Right. Unfortunately, this expression is not that useful to us because we skipped some steps. We skipped some steps earlier, right? And so this B right here, even though it's just a constant, at this point, it's still unknown. So by itself, this expression is basically useless to us unless we were to find out what that B actually is. Okay. But we can work with this. Okay. Because now we know what the optimum radius is. Okay. So this in sense, this kind of created a new variable for us. That's something we didn't have before. So before we had just kind of general radius, but now we know that if the radius equals this, then this is kind of the optimum of what it can be. Okay. So this derivation is kind of, we kind of go, kind of back and forth a lot of times, but we're almost done, I promise. And so we're going to take this expression. And what we're going to do is we're actually going to solve it for Q. Okay. Let's go ahead and do that. And so let's go ahead and raise both sides to the 6th power. And so we have R optimum. The 6th power is equal to pi squared B divided by 16 mu times Q squared. Okay. And so if we move the 16, oh, I reversed it already. Sorry, the 16 mu is up top. And so we have 16 mu divided by pi squared B. Sorry about that. Okay. Got ahead of myself a little bit. All right, now we can take this expression and we can solve for Q. Okay, so we're going to multiply both sides by pi squared B divided by 16 mu, and we're going to take the square root. Okay, and so we get Q is equal to square root pi squared B divided by 16 mu times R optimum raised to the 3rd power. And so at this point, it kind of seems like we're just pushing terms around just because, it seems like Dr. Tran just likes doing algebra, which is true. I do like doing algebra, but there is a purpose for all this. So let me circle this term in under the square root here, okay? It looks just like a collection of just random terms. In a sense, it is. But if you look at the nature of all the variables in this term right here, okay, you'll see that none of these variables depend on a specific blood vessel. Okay. So the first variable we have there is pi. Pi is just pi, right? So no matter if it's in a blood vessel, it's apple pie, whatever. Pi is always going to be 3.14159, right? So that's effectively a constant. Okay. We've already talked about B. So B is a fluid mechanics constant that depends just on the geometry, but it doesn't depend on the size. So that's effectively a constant as well. Okay. 16 is just 16. And then we have the viscosity mu, right? And so the viscosity we're going to assume is constant throughout the entire blood vessel, right? So everything that I've circled there in red, does not depend on a specific vessel, whether you have a parent vessel, daughter vessel. It doesn't depend on how big your vessel is. That term is always going to be the same. Okay. We don't know what that term is because of B, but at least we can say that it's a constant. Okay. And so what I'm going to do is I'm going to replace this with another constant. I know we're like playing alphabet soup here. We're running out of letters to use here. Okay. But this is mostly just to save yourself some writing, right? Because we know it's a constant. We don't know what it is. So let's just call it K. We could say that the flow rate inside a vessel is equal to K times the radius cubed. These circles. Okay. All right. There's only one more step, I promise. And the last step is it's pretty easy. Okay. All right. Any questions on this so far? All right. So what we have here is we have Q is equal to K times the radius cubed, or optimal radius cubed, okay? Right. Essentially what this is telling us is that the flow rate, or the volumetric flow rate in the blood, is proportional to the radius cubed. Okay? Let's use that information. So let's go back to our bifurcation. Okay. That's where we all started before the math nation kind of took over this lecture. Okay. So we have radius of the parent vessel, radius of the daughter vessel. Okay. And let's go ahead and lift that assumption. So we'll assume that the daughter vessels have different radius. So I'll call it RD1 and RD2. Okay. Not only that, but we have the flow in the parent vessel, QP. Okay. We have flow, and then we have flow in each of the daughter vessels, QD1 and QD2. Okay. And so what happens, in terms of fluid mechanics is that when you have flow coming in, that flow is going to split into the two daughter vessels. Okay. Okay. So we can use this information. We can say that even when a flow splits off, okay, the amount of mass must be conserved. And so the amount of mass coming in must equal the amount of mass coming out. Okay. So the amount of mass coming into this bifurcation is QP. Okay. And the amount of mass going out is the flow from the two daughter vessels. So QP must be equal to QD1 plus QD2. All right. So now is where it all comes together, right? So we know that from the past 30 minutes that flow rate is equal to K times the radius cubed, right? So let's plug in for that. So we know that QP is equal to K times the radius of the parent vessel, RP, Q, right? And we can do the same thing for the daughter vessels too. So QD1 is equal to K times RD1 cubed plus K times RD2 cubed. Okay. So all I've done is just I've substituted in the expression for the flow rates. Okay. All right, so what do we notice here, right? Every term here has K. And what we've said is that K does not depend on the specific vessel. It just depends on fluid mechanics in general. And so what we can do is we can cancel all these Ks, okay? Because they're all the same, right? It doesn't depend on the vessel. And then finally, we arrive at, a very simple expression that took us, I guess coming back from last time, almost a full lecture to do. Okay. Which is this Murray's Law relationship. Okay. Okay. And so Murray's Law states that, based on fluid mechanics and energy, energy minimization principles, that if you take the cube of the parent radius, that must equal to the sum of the cubes of the daughter radius. Okay. So you have RP cubed is equal to RD1 cubed plus RD2 cubed. Okay. Right. So, based on this, there is a relationship. So there is a relationship based on how flows will bifurcate. Okay. And the size of the vessels that form the bifurcation must follow these rules to kind of help with the energy properties. Okay. Any questions on this result here?
This applies to the human, well, I'm assuming to most animals, but like
Yep.
they found the sweet spot.
Yep. Yep. Yeah, pretty fascinating actually that it applies to a lot of well, there are deviations to this, and we'll talk about that in a second, but for the large part, things stick pretty close to this relationship. All right. So that's Murray's law, right? And so this is applicable to not only humans, but but anything with anything with pressure driven, energy driven flow. Okay. All right. But there are some caveats. So I guess before the caveats, let's start with an observation. Okay. So notice that the key number here is an exponent of 3, right? And so the radii of the parent and daughter vessels are related by the cubic power. Okay. What this means is that every time a vessel bifurcates, the total amount of surface area or the total amount of cross-sectional area is going to go up. And so to show this, let me show you if that exponent were 2 instead. Okay. And so if that exponent were 2, we'd have RP squared is equal to R D1 squared plus R D2 squared. Okay. And so if that exponent were 2, this would be something called an area conserving relationship. Okay. And so the total cross-sectional area is the same. So you basically just take the area and you just kind of split it in 2. It doesn't have to be in 2, but the total area has to be conserved. So that's not the case. And so what this basically is telling us is that, if you conserve the energy, if you conserve the area at a bifurcation, that's not energy efficient. So every time you split, and if you conserve the energy, you're going to be spending, proportionally kind of more energy than you need to. Okay. And so what this also means is that as you bifurcate more and more, your total kind of surface area for flow is ever increasing. Okay. So as you get further away from the heart, or as flow gets further away from the heart, and it not just increases, it actually dramatically increases. Okay. Because bifurcation is not something that just happens a few times in your body. It happens, millions and millions and millions of times. And so, if you imagine every time you bifurcate, you're increasing the amount of the cross-sectional area, just because of the way of power of scales and everything, this dramatically increases it. Okay. And so I think on the second day of class, we talked about the cross-sectional area of your aorta. So your aorta is the biggest blood vessel you have in your body. It's the first blood vessel that kind of comes out the heart. I think the diameter of the vessel is like anywhere between 2.5 and 3 centimeters for the average person, which is really small. But as you get further and further away from the heart, that total area increases quite dramatically because of the bifurcation and because of Murray's law. Okay. And what we'll see, as we get into the next set of lecture notes, that has a lot of effects on the fluid mechanics in terms of the total amount of flow, the velocities, things like that. Okay, so it's a very, very interesting phenomenon that occurs. All right, number two. Number 2 is a caveat. So, this whole Murray's law and this whole derivation that we went through, it depended on a lot of assumptions. Okay? Most of the assumptions we talked about when we did Navier-Stokes last week, but let's kind of remind ourselves what those assumptions are. And I won't list all the assumptions because they're not all particularly relevant here, but I'll list the ones that are most relevant. So in particular, this law here depends on steady flow. Okay. And so we made the assumption that the flow is steady within our blood vessels, which we've already talked about is not true in general because of the pulsatility of the heart. Okay. And it also depends on rigid walls. Okay. Which is also not true because we know that your blood vessels are flexible structures. Okay. And so what this means is that, if you actually measure, so people have actually measured, the radii of blood vessels in humans as they bifurcate at lots of different areas of a person's body, and they found that the exact law that the vessels follow deviates depending on where you are. So depending on where you are in the body, depending on where the vessel is, you're going to have deviation. But what's interesting is that, it still follows the same basic idea. Okay? So no matter where you are in the body, we have the same basic relationship where we have RP is equal to RD1 plus RD2. Okay. And all of those quantities are raised by the same exponent. Okay. And so in the basic Murray's law, that alpha there is 3. Okay. But for other parts of the body, that exponent tends to vary. Okay. So I have a table here that kind of shows you. And I classified this by the diameter. Okay. So depending on the diameter of the, I should say parent vessel diameter. I don't know why I have this listed as diameter, but then the equation's in radius, so just be a little careful about that. Okay, so for the diameter, if your vessel diameter is between 0.2 and 0.5 centimeters, okay. So these are generally a lot of the larger arteries that you have in your body. The value for alpha is going to be between 2.4 and 2.65. Okay. Alpha is dimensionless because it's an exponent. Okay. And what you'll notice from these ranges is that they're not all encompassing, so there's going to be gaps. And so, there's, of course, these are all kind of just approximations. And so the next range here, we have 0.05 or 0.025 to 0.05 centimeters. Okay. So you can see there's a gap between the first range and the second range. So this ranges from anywhere between 2.65 to 2.9 for the value of alpha. Okay. So those are kind of the smaller arteries that are still typically visible to the human eye, but they kind of get harder and harder. All right, so the next range we have is 0.0005 to 0.025 centimeters. Okay. So we're starting to get in the range of capillaries, but not quite there yet. And so the values for alpha in this range is 2.75 to 3. Okay. And then finally, we have the capillaries. So these are the ones that are kind of essentially invisible to the human eye, a little bit too small. So these are vessels with diameters less than 0.0005 centimeters. And once you kind of get down to that level, that's when Murray's law is kind of satisfied in the best. Okay. All right. So generally speaking, as the smaller your vessel gets, the more closer you kind of get to the ideal conditions set about by Murray's law. But the bigger vessel you have, the alpha value kind of deviates from that. It never gets down to 2. I think for the aorta is the biggest one, and I believe when I was doing research, I used alpha. I think 2.3 is what we typically use. So it never gets down to 2, but it kind of hovers in that like 2.3 to 3.0 for that. Any questions on this?
Is there an overlap between? Is that 2.75 to 3?
No, yeah. So there's yeah, there's some gray area. So there's not perfect overlap between these. These are all just kind of approximate measurements based on data. Yeah. Any other questions on this? Okay. Ooh, so this took a lot more time than I thought. Let's go over one more thing before we sign off for today. Okay, so the last thing I want to talk about today is the concept of wall shear stress. All right. So we've talked about we've mentioned this today already, actually. So when we were talking about viscous friction forces, this is essentially what we call it. So kind of the more I would say the more scientific term for viscous friction forces is wall shear stress. Okay. So the wall shear stress is the viscous drag force that any fluid experiences So whenever you have a fluid that flows past a solid object, okay, that solid object is going to impart a viscous drag on it, okay, and so we call that the wall shear stress. And so for blood flow, the wall shear stress is imparted literally by the vessel walls, okay. All right, and so we can compute this. Okay. So the formula for viscous shear stress we've already talked about before is mu, which is the velocity, multiplied by the derivative of the velocity, okay? So mu here, this is the viscosity. Okay. And then uz, this is our velocity solution from Navier-Stokes. Okay. And so just to kind of refresh your memory, what we found from Navier-Stokes is that uz is equal to 1/4 mu dp dz times little r squared minus big R squared. Okay. All right. Oh, one important thing. So when you take the derivative, after you take the derivative, you're going to set little r equal to big R. Okay. So you're basically evaluating the velocity derivative at the wall. So evaluate. Okay. Okay. So this part's pretty easy. You're just taking this expression here on the right. We're taking the derivative with respect to little r, plugging in big R. Okay. And so we get tau W, or the wall shear stress, is equal to R/2 times dp dz. Okay. And so just like we did in the derivation of Murray's law, let's put this in terms of Q. Okay. Because if we put things in terms of Q, we can make use of conservation of mass. That kind of gives us access to another equation. Okay. And so in particular, I want to take this dp dz and put this in terms of Q. I want to substitute okay. I want to substitute an expression that has Q. Okay. All right. So luckily, we already have an expression that relates Q to dp dz. Okay. And it was from last class. And so what we found from last class was that Q is equal to minus pi r to the fourth divided by 8 mu times dp dz. Okay. And so if we solve this expression for dp dz, what we get is dp dz is equal to minus 8 mu q divided by pi r to the fourth. Okay. Bless you. All right, so let's take this expression here and plug into the wall shear stress. Okay. And what we get is how W is equal to 4Q. I'm going to ignore the negative for a second. Just the negative just indicates the direction for the wall shear stress, but we're just going to look at the magnitude. So I'm just going to ignore that negative for now. Okay. So we get the wall shear stress is equal to 4Q times mu divided by pi r cubed. Okay. And let's do that. This is the wall shear stress. Wall shear stress in a cylindrical vessel. Okay. Yeah. Yeah, so I'm just ignoring the negative for now because the negative just indicates direction. And so so we're just looking at the magnitude here. It's there, we're just ignoring it for the sake of simplicity. All right. So the last thing I want to do today is I want to take this result here and notice that it has a lot of the similar players that we've been talking about a lot today. So it has Q, it has the radius. It has radius cubed, which should which might give you a hint of kind of where we're going with this. But let's take this and let's relate it to Murray's law. Okay. What you're going to see here is that we're going to get a very, very interesting result from this. Okay. So for the sake of time here, I'm going to simplify Murray's law a little bit. Okay. And so let's just for the sake of argument, let's assume that both daughter vessels are the same size. Okay. And so Murray's law, remember Murray's law is RP cubed is equal to RD1 cubed plus RD2 cubed. Okay. If we assume that both daughter vessels are the same, then we get RP cubed is equal to, then we're just gonna have one RD. RP cubed is equal to 2RD cubed. Okay. The other thing we're going to have is we're going to have conservation of mass. Okay. And if we assume that both daughter vessels are the same size, that means the flow within those daughter vessels are the same. Okay? So that means we have QP is equal to 2QV. Okay. Okay. So let's take these, okay? Because we know through Murray's law and we know through conservation of mass that the parent and daughter vessel radii are related through this arrangement, okay? So let's compute wall shear stress in the parent and daughter vessels. So let's do the daughter vessel first. That's the simple one. All right. So for the daughter vessels, we have tau W, the wall shear stress is equal to 4 times the flow rate in the daughter vessel. So the flow rate in the daughter vessel is QD, okay, times mu divided by pi RD cubed, okay? Okay. So we're going to use the daughter vessel as kind of the reference here. Okay, so we're going to leave the daughter vessel expression alone. Okay, so let's compute the same thing for the parent vessels. For the parent vessel, we have tau W is equal to 4 times QP times mu divided by pi RD or RP cubed. Sorry. Again, my P's and D's mixed up. Right. But we can plug in for QP and RP, right? Because we know that QP is equal to 2 times QD, right? And we know that RP cubed just happens to be equal to 2RD cubed. Okay? So let's plug in for those. So 4 times QP, so QP is 2 times QD times mu, okay, divided by pi. RP cubed is 2RD cubed, okay? Right, so all I did there was just plug in for QP and RP cubed. Okay. We have a 2 that came out on top. We have a 2 that came out on bottom. So let's just cancel those two 2's out. Okay. And so what we get is that we have 4 QD times mu divided by pi RD cubed. Okay. Okay. And so if you compare that to the wall shear stress that's in the daughter vessel, you should probably notice that, huh, that looks familiar. They're exactly the same. Okay. So this is cool. So based on the Murray's law, so based on the radii relationship between the parent and daughter vessels, this means that the viscous shear forces in both the parent and daughter vessels are exactly the same. Okay. So you can see here the Murray's law serves another purpose. So not only does the Murray's law, important for energy conservation, it's also important for kind of a concept called homeostasis, right? So homeostasis, that's a term that we're going to go over a lot in this class. Basically, what homeostasis means is that the cells inside your body, they kind of grow accustomed to their physical environment, and so that includes kind of the forces that they're exposed to. And so it doesn't really matter where you are in the cardiovascular system, the cells that are inside your blood vessels, they want to kind of maintain that same viscous shear force, right? And so the Murray's law kind of helps them achieve that. And so there's a lot of kind of applications for this in terms of disease, in terms of device design, and in terms of a lot of stuff. But so this is kind of just the first wave of that. But very, very interesting, very fascinating result from this. Any final questions on this before we wrap it up for today?
Is this like the shear stress is only uniform, assuming the assumption that they're like both equally
Exactly.
and so rigid?
Exactly. Yeah. So it doesn't work out exactly like this. So you don't have perfectly uniform shear stress all throughout your body, but it tries to kind of equilibrate. So it's kind of an equilibrium type of situation.
So it could be like kind of more true for like your capillaries in there.
Exactly.
So since they're so negligibly small.
Exactly. Yeah. Yeah. And that's really important for nutrient transfer, so like oxygen transfer. You want to make sure that the condition, all those capillaries is exactly the same. So this kind of helps with that as well. Okay. Any other questions on this? Okay, all right, so that's all we got time for today, and so we'll pick this up on Thursday. So on Thursday, we'll talk a bit more about the biology. We'll take some of these results and see how that applies to biomechanics, and so that'll be really interesting. So thank you guys for coming today. Stay dry, stay safe. If you're driving today, make sure you drive really carefully. It's really wet on the roads right now, so you don't want to hydroplane and have that stuff happen. So, thank you guys for coming today, and I'll see you Thursday.
Given this, wouldn't the, would us suspended split the daughters equally all the time? Because otherwise the shear stress.
It's this shear stress thing, it's a preference, but it's not a requirement. So it's actually, so you do see variances in shear stress at different parts of the body, especially when you have pulsatility, take pulsatility into account. But it tries to kind of equilibrate kind of around the same value. Yeah.
So why would the body split the, vessels differently? Would it be just to get more blood flow to a certain?
That's part of it. Yeah. So some areas of your body have different demands for blood flow, and so you may have bigger vessels there to make sure the more blood flows down that way. Some your capillaries aren't all equal too, so some have kind of greater demands than others too. So yeah, a lot of biology kind of factors into this as well.
Yeah.
Mhm.
Does the body take some? Yeah, but the rest of the. Hope don't have gross stuff though. You just put that up there.